Hello, and welcome to this presentation on Lab number 5, presented by Group 13. Group 13 is, well, me, John Bake. In the presentation, we will look at the purpose of the lab and the conclusions drawn from it. We will also walk through a step-by-step explanation of the parts of the lab process that was used. The purpose of this lab is first to allow us to become familiar with SR or SC latches, gated D latches, and D flip-flops. We will also discuss how to find timing information on a datasheet for a specific IC. The lab also gave us practice in understanding and implementing a transition table. In part 1 of the lab, we examined an SR latch that was constructed using NOR gates. We first used a transition table to determine the expected outputs for each input combination. The transition table is similar to a truth table, but it reflects the change or delta in the output state as Q+. In this circuit, S is the set input, R is the reset input, and Q is the current output state. We expect a high value on S to set Q+, or the output, at high. A high value on R will reset the output to a 0 state, and when neither one is asserted, high, the output retains its current state. Because the circuit's output is also used as an input to the circuit, having both the S and R values high presents a problem. The circuit's output and its complement in this case will be the same, which negates the purpose of the circuit. This is why we have NAs in the last two rows. The next step in the lab process was to construct a simulation of the circuit to validate the expected results. This testing can be a little tricky because the Q value must be set prior to changing the S or R inputs. It is also important to note that the Q output is located at the bottom of the circuit. We can see that each simulation matches the value in the transition table. This is the final two expected results, and we can see in that first one that when the value is changed, the value on S is changed, we get a value of 1 on Q. We can also see the issue with both S and R being high. We get 2 zeros, and this is not desirable. Next, we performed the same exercise with an SR latch that was built using NAND instead of NOR gates. With this configuration, it is the low value, or the 0, that impacts the output state, not the high or the 1. Again, a condition where both are low is undesirable, as we can see in the first two rows. Building and testing the circuit proves the results we expected are correct. In addition to the use of the low asserted value, this circuit differs from the previous one in that now the Q output is at the top of the circuit. Because the set and output are now visually tied together, this gate might be slightly easier to understand. In part 5, we looked at a D latch. As we will see on the next slide, this latch consists of 2 ANDs, 2 NORs, and a NOT gate. The D input represents the data that is fed to the circuit, but it cannot impact the state until the gate is triggered. Thus, we only expect the Q value to change when the gate input is a 1. This can be seen in the last 4 rows, where Q takes on whatever value is asserted on D, whereas in the first 4 rows, the Q value remains the same. Our simulation of the circuit again proves the results are as expected. We only see changes in the output state when the gate is asserted high. After manually simulating the circuit functions, we performed an automated test of the simulation and verified our results. We can see the results here with the 3 circuits. Part 8 of the lab allowed us to examine another circuit, the D flip-flop. Similar to the D latch, this design only allows the state of the output to be changed, except in this case it is when the clock cycles. More specifically, it is when the rising edge of the clock cycle hits, which allows the input from D to be stored in the flip-flop. We validated that the D flip-flop operated as we expected. Additionally, we experimented with the use of the enable, preset, and clear inputs on the flip-flop. The enable will allow the data value to affect the state only when it is high. The preset immediately sets the output to 1, and as long as the preset is asserted high, it keeps it at 1. Likewise, the clear will set the output to 0 in the same manner when it is asserted high. If both are asserted high, the clear has precedence over the preset. In noise in the signal, which may lead to unexpected behavior in the circuit. This is shown in the bottom left diagram. We finally looked at the timing specs for two ICs. First we have a D flip-flop, and second we have a decoder. With the first, we can see that the fastest the clock can cycle is 25 nanoseconds. This is because the required setup and hold times of the circuit add up to 25 nanoseconds. It is interesting to note that the state change from low to high is almost twice as fast as the state change from high to low for this circuit. Whereas for the decoder, the propagation delay is exactly the same, but the times are much longer. In conclusion, while we ran into no issues in performing the exercises for the lab, we found several conclusions. To design a functional circuit, it is important to understand the timing limitations, especially as the complexity of the circuit grows. The big takeaway is that we are now seeing further basic circuits that are the building blocks for most of the parts in today's computing equipment. Thank you for viewing our presentation.